Please welcome to the stage, John Dodaro.
Hello? Does this go backwards? Okay. Yep. So hi, everyone. Thank you for the opportunity to talk about the work that we've been doing. I wanted to start off with a little bit of background about myself and our team. So my name is John Dodaro. I'm from New York. Maybe you could tell from the way I talk. Went to Columbia for my undergrad in applied math, but my passion was always for physics. Moved west to Stanford to study physics for my PhD program, and my goal was to work on the theory of everything, an equation you could put on your shirt and it would describe how the whole universe works. So I started in a quantum gravity group, and after about a month I said, this is enough for me. There's too many questions of Alice and Bob falling inside black holes, and a lot of what I considered to be beyond the limit of testability. I was much more interested in what Wolfgang Pauli would affectionately call the physics of dirt, as Florian told us yesterday. My work was in theoretical solid-state physics, high-temperature superconductivity, shown here, high-temperature superconductor. I think there's a lot of insights that we could learn. Carl did make the analogy yesterday from these two different fields. Both have been around for around 30 years, and there's still some foundational questions about underlying theory and mechanism, as well as lessons that I think we could learn about materials control and variability when dealing with complex systems and complex materials. But I had stumbled on some work by Schwinger, which I'll talk about more, that got me interested in cold fusion. I started reading the literature, learning a bit more about the history, and took a course at Stanford taught by this fellow, Ricardo Levi. Ricardo has a background in catalysis. He was a businessman, entrepreneur. He started a company called Catalytica, ran it for 25 years, took it public, eventually sold it for $1 billion, and now pays it forward, teaching a course at Stanford on energy entrepreneurship. And so I talked to him and said, I'm interested in cold fusion. It's very high risk, but very high reward, as is clear to everyone here. But we have some ideas. I have some ideas motivated by the theory, motivated by some experiments, and maybe we could throw our hat in the ring. What do you think we could do? And so he said, well, let me introduce you to my first hire at my company, Catalytica, our brilliant experimental mind, Ralph Dalabetta. He's on maybe 50 patents, dozens of publications, a brilliant technical thinker and tinkerer, as you can see here in his natural habitat, soldering or doing something at the kitchen table. So very much a tinkerer, extremely technical, and complementing my own maybe theoretical background, we said, why don't we start a company, raise some money. We formed Aquarius Energy with the goal of de-risking the science. We're venture-backed, so raise some money to do experiments with a group that has a very long-term time horizon, that cold fusion is something actually palatable to them. They could understand the risks associated with it, but also the reward. And so we said, let's partner with Stanford. We sponsored a research agreement under the direction of Professor Matteo Carniello, a young up-and-coming professor at Stanford in the chemical engineering department, who specializes in nanomaterials and tailoring nanoparticles for energy applications, understanding their role in catalysis, combustion, and so on. We worked with a postdoc, Andrew Risco, formerly in the group, who led a lot of the development on the synthesis and recipes that I'll describe to you, as well as a very capable master's student in the material science department, Kai Goodman, who's taking up a lot of the work on the synthesis and running the experiments. And so that's our team. And the rest of the talk will be divided into two parts. The first, theoretical. In the absence of a complete theoretical framework, something that we've talked about already at this conference, how can theory help us? How can it guide us? So that's coming from my own background. And then the second, talking about our experimental approach to what we call an IPP, an irrefutable proof of principle experiment. So where we are in setting that up. So let's start with theory. So this is one of my favorite cartoons from a book on Feynman diagrams. You can see the real horse and the quasi-horse. And this highlights the difference between maybe a single particle thinking and a many multi-particle thinking, or many-body machinery that we need to describe more complicated systems. And so when we're thinking about high-temperature hot fusion in the sun, we like to think in terms of the real particle. Simple collision, two horses crashing into each other. The horse has a mass. We could describe its properties, how it's moving. But when we go down to low energies, in particular, we're looking at the lattice, we need to expand our thinking and expand our machinery. And so here you can see the quasi-particles. When there's many interacting degrees of freedom, form the quasi-horse. And so it's still horse-like. It has horse properties. It has a new type of effective mass. But we have to use that more complicated machinery of many-body thinking when we go to the low energy scales characteristic of the lattice. And the first person to highlight this that I read about was Julian Schwinger in the context of cold fusion. And so he pointed out for high energy reactions, we can think of the fusion rate as a product of the electromagnetic piece, what's the tunneling probability over the Coulomb barrier, and then the nuclear piece, what's the sticking probability. So overcoming that barrier and then sticking, that works well in the two-body process at high energy scales where we can work with the real horse. But at low energy scales, the problem becomes more interesting and more complex. The lattice degrees of freedom can play a role, and so he studied the fusion rate in terms of a vacuum decay. So starting with a system of, imagine, 0 phonons, you have a decay, a nuclear event that transfers energy and creates a large number of phonons. And so this requires a large number of phonons because they are low energy degrees of freedom. It's a coherent many-body process, but it's the type of thinking that at least got me interested in the field from a theoretical perspective. So of the myriad monikers, I think we've already heard a large number of ways of describing why we're all here today. Cold fusion, Lenner, different names. I've opted for lattice catalyzed fusion, and just to emphasize why, going back to the Schwinger work, he highlighted 2 relevant scales in the lattice, at least 2, if we could really simplify the problem. The first, let's call it R0. It's the DD separation inside of the lattice, here shown between 2 octahedral sites, a roughly 1 angstrom scale. And then a second lattice scale that comes in, let's call it lambda. I call it for simplicity smearing. You could imagine it like the 0-point motion in a quantum harmonic oscillator well. The bottom there shows the ground state. So these are the 2 scales in the lattice, and their interplay can become important, and it does factor into his calculation. Just to give you a sense of scale, the environment is what's determining the wavelength. And so if you imagine 15 million degrees in the sun, and we compute this thermal wavelength, we see it's quite small, 0.0005 angstroms. But when we go to low energy systems, because the lambda depends inversely on the square root of omega, when we look at a hydrogen molecule, or more interesting to us, optical phonons, we see that scale reaches around 0.2 angstroms, which starts to get within a stone's throw of this R0 quantity at 1 angstrom. So that's why the lattice is interesting. Lattice catalyzed, well, a catalyst can increase the reaction rate. It could lower energy barriers, create intermediate states, direct us towards certain pathways. And so that was the choice of wording of our myriad monikers. But what struck me about this calculation by Schwinger is that despite being an incomplete theory, still very open questions about mechanism, it does provide a simple prescription in terms of these 2 parameters. We want to minimize R0, because we're talking about fusion at the end of the day. We do want things to overlap, and increase smearing. So get close and smear is the simplest way of putting it to maximize the probability of a reaction in this system. And so to be a bit more quantitative, here's an example of a numerical calculation. So taking Schwinger's result and just extending it for different parameters. And you'll notice a strong sensitivity to this ratio, lambda over r. And so what we're plotting here is the reaction rate inverse seconds as a function of this smearing lambda in angstroms. The different colors represent different values of R0. So the green would be filling up octahedral sites. So that's the separation between 2 octahedral sites. The yellow is an octahedral tetrahedral separation, and the red is 2 deuterium atoms hopping into the same octahedral well. So a very high energy configuration, not an equilibrium configuration. And then the blue line represents what we can think of as an upper limit. It would be the pure hydrogen molecule taken outside of the lattice. But the moment we bring hydrogen inside of the lattice, it shares electrons, and so we can't really hit that distance. So for the purposes of the calculation, think of that as an upper limit, and we would want to strive ideally towards something like the red line. So to orient us on this plot, let's consider a couple points. I took this from the neutron powder diffraction, the Debye-Waller factor, which tells you how the scattering peak gets broadened, and it gives us a length scale. And so for palladium deuteride, here's the alpha phase and beta phase, 0.06 and 0.2 angstroms. And that's what we're plotting to around 0.3, so say a 50% enhancement of this beta phase lambda. And on the vertical axis, we're plotting another point here, our threshold of 1 watt per mole. And so this is at least an intuitive number that we can look at, because this is a wide range here, 40 orders of magnitude. This is a ballpark estimate of what we would need to see heat level. So not just low levels of nuclear products, but be above this threshold for heat. And this is a calculation from a particular model. You should take it with a large grain of salt. But if we were to interpret this at face value, what you would notice is that even at 0.3 of this smearing, we're still below the threshold for the green line. And so that would even suggest going to a one-to-one loading. Filling up all of the octahedral sites is still insufficient to generate heat. So you need to kick your system or get out of equilibrium to cross that threshold. So that was an interesting result that really struck me from the early days, and I think provides some guidance on engineering systems by maximizing this ratio of lambda over R naught. But we can go further and ask, what is the actual distribution of lambda, of smearing in our systems? So this is based off an unpublished calculation by Steve Koonin, actually a paper that Florian brought to my attention. I hadn't stumbled on it before. And it's a pretty neat calculation. So he considers a shifted Coulomb potential. We heard it before about how screening can factor into this, and so that's sort of what this calculation represents. You could shift your bare Coulomb potential by a screening energy V naught, and that's plotted on the horizontal axis. And on the vertical axis is the tunneling probability. And so here we're looking at different reduced mass, so H plus D or D plus D, as a function of this screening energy. And as you could see, you turn the knob, increase the screening energy, and the tunneling probability takes off. In green is the classical separation distance. So as you reduce this barrier, it's much easier to get a classical turning point that's a lot smaller. And what Koonin did was, starting with this equation, or this numerical result here, he said, what happens if we introduce fluctuations in this parameter? What if it's not a uniform screening value, but it's a distribution of screening values? And the idea is that because of this exponential sensitivity the tunneling probability has to this screening energy, a small increase in the screening energy results in a large enhancement of the tunneling probability. And so there are rare configurations where you have a large screening energy that can overwhelmingly contribute to the net effective reaction rate. And so that's what's plotted on the right side. So this is reaction rate enhancement above the bear case without fluctuations. And you can see it goes over a wide range. These dashed lines on top represent the theoretical upper limit, so that would be like a transparent barrier. And then the dotted lines represent taking a base screening energy of 31 electron volts, so roughly for a hydrogen molecule. The solid lines are taking a higher energy one, which we saw in the previous slides may not be unreasonable for palladium systems, 300 electron volts. But the key takeaway here is that when we start turning on fluctuations by tuning across this horizontal axis, that's increasing the strength and range of these fluctuations. If you like, it's a Gaussian, so you're broadening that Gaussian. We see a large enhancement, 10, 20, 30, 40 orders of magnitude in the amplified fusion rate due to fluctuations. And so the takeaway here is that when we introduce fluctuations into our system, we could see large enhancements in the fusion rate. So that was the conclusion from this calculation. And so I thought, well, what if we put these two together? We take the result from Schwinger and then combine it with Koonin's insight about fluctuations, and that's this numerical result shown here. So on the left is Gaussian fluctuations. On the right, it's a more microscopically motivated model, power law fluctuations. But the result is the same. We see on the vertical axis the effective fusion rate inverse seconds as a function now of strength of fluctuations. And so we increase the strength of those fluctuations, and we see in all cases we can cross this threshold more easily. And so the particular numbers here, again, don't matter so much. I won't go into the details, but I hope the takeaway is clear, is that when we introduce fluctuations to our system, we can enhance the tunneling probability significantly and the effective overall fusion rate. And so with this in mind, we can ask, how can this theoretical underpinning help point us in a direction towards useful R&D and actually engineering a system? What can we learn from these insights, even if it's not a complete theory that explains everything? And so in that spirit, we came up with 3 components. So one is this non-equilibrium stimulation. How do we kick the system out of equilibrium to enhance the probabilities? 2, we wanted to work with nanoparticles, a high surface area, maximize the amount of flux going in and out. And then 3, when you're dealing with nanoparticles, you don't want them to sinter. One comes to its neighbor and they form a big blob, and you lose the nanoparticle nature that you worked so hard to achieve in the first place. So how do you couple that to a support that won't be destroying the very nanoparticles you created? And so it turns out there's some experimental precedents for these ideas. We're not the first to think of stimulation. This was also mentioned in the previous session. Here's a plot of excess heat as a function of infrared beat frequency. This is work from Hagelstein, Letts, and Cravens. And they show there's an apparent enhancement of excess heat at frequencies that appear to line up with the phonons of palladium deuteride. So that's the stimulation component. Second is nanoparticles. Again, we're not the first to think of nanoparticles. There's been large excess heat reported in alloys. Here they're coupled to ceramics. This is work from Japanese groups, the NITO report. Third, we're doing something a bit different in the heat removal component. And so ceramics are nice. They have high thermal stability. But for our purposes, we wanted to look at carbon nanotubes. So carbon nanotubes have the highest thermal conductivity. The only thing that comes close is diamond, an allotrope of carbon. But we'd have the high thermal conductivity and high thermal stability that could form a good heat sink for our catalysts and then couple it with our nanoparticles. So that was the theoretical motivation to guide our program. Now I want to tell you a little bit about where we are in setting up the experiment for what we call, again, the IPP, an irrefutable proof of principle experiment. And so in assessing the field, we had our own perspective on what we thought were the problems that we would like to address in showing that there is a there. And so the first one was the focus on measuring heat. It was our opinion that that's indirect for hypothesis validation. What we really want to do is see nuclear ash. And number two, the uncontrolled materials variability was a big issue that we wanted to address in our approach. And so the two solutions that we used to guide our program were, number one, target the smoking gun, look for helium in our case. And number two, introduce a strong level of control and characterizing our nanomaterials so we're confident what we're putting in our reactor each time is the same and reproducible in that sense. So here's a little cartoon of what our IPP approach looks like. We have deuterium or hydrogen gas flowing into our reactor. We have a window where we zap it with the lasers. We have our catalyst layer and some detectors in there measuring temperature and even high energy charged particles. We can control the temperature with heat, and then downstream of the reactor we have a high resolution mass spec. So this is our crown jewel in the lab. And as it says on the bottom, we're trying to validate this hypothesis with these three detectors. So focused on helium, number one, but also correlating it with these other indicators, so temperature rise, and then energetic particles, which would be indicative of a nuclear reaction, especially in the MeV scale. So to break down the different components here, let's start with the nanoparticles. So this is our state-of-the-art approach to colloidal synthesis. It's the expertise of Professor Matteo Carniello's group at Stanford. If you want 2 nanometers, we'll grow them all 2 nanometers. If you want 7 nanometers, we'll grow them all 7 nanometers. We really have control over the size distribution here. And we can tailor the nanoparticles in terms of composition, shape, et cetera. And so what you're seeing here is an EDS spectrum of the different components. So this one is a palladium-nickel mixture. And so by measuring the ratios, we can tell what that composition is. And we take these particles and then combine them with our support, so carbon nanotubes. We have a million of these pictures, but I just wanted to give you a few that are representative of what we can do. We have different quality nanotubes, so we could put the particles on top of the nanotubes. We could put them inside and clog up the nanotubes. We can put a high weight loading density on the nanotubes, very small particles, a highly, in a very busy environment you could see there where sintering can be a risk. But even in the bottom right, you could see we could play with different layers. So this is core shell nanoparticles. We can form a palladium surface with a nickel core with a palladium surface, and play around with tuning our materials at the nano level and making sure that we characterize them so we know what's going in each time. So this is what our little reactor looks like. We start with our catalyst. The nanoparticles or carbon nanotubes are very powdery, so we had to come up with a recipe for a wash coat. It's like peanut butter. We put it on our sandwich bread there. That's a substrate, which has some temperature sensors, so we can record temperature data in real time with the RTDs. We got a silicon alpha detector. It detects charged particles, so the glorified solar cell, really. And we took apart a smoke detector to get a little bit of americium to calibrate our detector, which Stanford was not very happy with us taking apart. But in any case, it gave us a calibration down to 100 nanowatts of these detectors. And lastly, we have our laser components. So these diodes are solid-state diodes, a couple of watts. And we do something similar to the dual laser experiment, turning on 2 of these at a time in hopes of creating a beat frequency on the surface or in the nanoparticles. You can see the little reactor has a window here where we zap the catalyst, and we built our enclosure to make sure that Stanford was happy with us sending lasers in every which direction. So that's the enclosure that goes on top of the cell and allows us to run these tests. So in terms of the actual detection for us, profile equals proof, meaning the mass spec profile is what constitutes the smoking gun for our approach. And so what we're seeing here is counts per second as a function of mass. And we could see very nicely E equals mc squared. That's wonderful. This giant peak on the right is deuterium because we are flowing in a deuterium environment. This goes way off the chart up to 10 million counts per second. And this little bump right next to it in orange is helium, which is what we're after. And you could see it in orange. The blue and green represent background noises, so this is for a calibration. And so you could see we can have confidence when there's the absence of helium, and then look for this small little bump. But because of E equals mc squared, we do need this high-resolution mass spec to be able to resolve this tiny peak next to deuterium and really believe that we're seeing helium produced in our system. So here's a typical example of what some data looks like, not particularly exotic, but that's partially why I wanted to show it. This is how it comes in. We see temperature plotted on the left axis. The RTDs are recording the data in blue. There's little pulses with the laser. I think at low power here, it's only a few degrees. But what we can do is pulse the lasers, turn it on, turn it off, sweep different frequencies, and automate that entire process to collect data. And then on the right side is the counts per second of helium, plotted in yellow points here, with a moving average in yellow, the solid line. There was this massive bump here. Unfortunately, that's not an anomalous result. That resulted from the mass spec pulling air. But it's looking at data like this that's giving us confidence in our measurements that we know when we are getting helium, and importantly, looking at these in real time to see correlations between the indicators, between the stimulation and helium in real time to have confidence in the results. If we really are focused on maximizing helium detection and increasing sensitivity, we could trade off that real-time piece, batch up our reactor, close off the valves, and let it sit for 1 hour, 1 day, 1 week, however long we like, and then in the hopes of building up helium over that time, sample the reaction all at once and see if we see helium. And so this was another calibration test. The green plotted on the right-hand side, that's nitrogen, so measuring air contamination on a log scale. And the blue and red correspond to helium and the background noise for helium. And so we start the flow, and you can see it levels off. And then we open up the cell that was closed before. We unbatch it, and we see a clear bump in helium, which decays back to the background level as the cell is purged with gases. And you could see there's not really a bump in air. It's on a log scale, so there's a little bump, but we've looked at enough of this that we have confidence there's no air contamination entering our system. And so we have the real-time analysis, we have this batch analysis, and by studying air, making sure there's no contamination, and taking this data and then looking at the profile information to really confirm, that's what constitutes a smoking gun, at least for our approach. So far, we've been relatively, I would say, scattershot in the tests that we've performed. Our focus was on the material synthesis, making sure we understand our recipes, as well as setting up the reactor, making sure we can rule out false positives. But in terms of next steps, this is the parameter space we would want to explore. We could divide it into 3 buckets. One is what the reactor is doing, so that's operating conditions. Pressure, we could go up to about 10 bar, 500 Celsius, and we could tune the hydrogen-deuterium ratio, which I think is at least something that I thought was a new component, tuning that smoothly between 0 and 1. A second is the catalyst composition, which we think is our specialty. Different synthesis approaches, controlling the diameter, the alloy composition, size, shape, what have you, the density of nanoparticles on the nanotube, for example. And lastly, the stimulation source, so laser frequency, scanning over these different terahertz frequencies to try and generate that beat frequency. So those are the 3 buckets we would like to explore. So to summarize, the IPP, an irrefutable proof of principle in our minds, does require that smoking gun evidence, that nuclear ash, to complement the work that's been done on excess heat and anomalous heat measurements. At Stanford, we've developed this library, our nanoparticle cookbook, of reproducible catalyst recipes that we worked hard to characterize them before and after, and really understand with our different probes that are available to us what our materials are doing, what they look like, and make sure we have control there. We are motivated by, I would say, first principles theory. Again, there's no complete theory here, but we try to use as much as we can theoretical insights to guide the R&D. And we've built a reactor that's focused on helium detection, in particular, looking at it in real time with the high-resolution mass spec. And lastly, in terms of next steps, ideally we want to expand the program to explore the key parameter space that I outlined earlier more systematically, more comprehensively, and look for helium signals that correlate with our stimulation and correlate with the different reaction indicators. So I hope that gives you a sense of what we're working on at Stanford, using some theoretical motivation to guide our experimental approach. So if you're interested in talking more, I'm happy to chat after. Please come find me. But otherwise, I'm happy to take questions. Thank you. Yep.
I'm Tom Paschal. I've been looking at having time to, now that I'm retired several years, I'm looking at literature and actually reading it. And it does impress me that many of the events seem to be correlated, that heat events, with the exiting of the deuterons out from being in the metal into the spatial region of the gaseous phase. How do you handle that kind of situation in your theoretical studies, or have you considered that as something you can always handle without any trouble?
Yeah, so thanks, Tom, for the question. I haven't considered it, I would say, at any depth theoretically. I think it's a good idea to consider. I mean, I would imagine some sort of traffic jam scenario as you're really trying to evacuate the deuterium. Beyond that, I haven't put too much thought into it. I mean, to our extent, we can control temperature over this small range, say 0 to 500 Celsius, which would be enough to deload the palladium, especially because these are nanoparticles. It does change the phase diagram. So I don't know how rapidly we can do that compared to other experiments, but it is an interesting point to think about. Thanks.
Rob Kimball with Solitic. Just wondering, are you working with any other labs on replication?
So no, not yet. I mean, I think as Matt had mentioned in the previous session, I think it's good to have teamwork and collaboration, so something we're definitely open to. At this point, I just wanted to talk about more the experimental setup. Not any sort of results yet, so I don't think we're even at that point of replication, but definitely open to talking with the community and partnerships, that sort of thing. Yeah, thanks, Rob.
John Brandenburg, Kepler Aerospace. I just want to first make a comment. I'm so glad that you're here from the high temperature superconductor field, because to me this is directly analogous to what we're dealing with. We have vague notions of a theory based on very low temperature superconductors that we can apply to the high temperature, but they don't, something is missing from our understanding. But would you agree with the statement that we can take the Julian-Schwinger model and also Peter's model of the downshifting of nuclear output to lattice thermal? These are all very well understood mainstream physics ideas. What is missing is a change in parameters on the mediation of the strong force. Some reason the exponential factors, there's a factor in the exponential factor that is changing. Would you agree with the statement that if you put that in as a free parameter, could you explain LENR, given the other posited models that are mainstream physics?
So thanks for the question, John. I'm not quite sure.
Okay, it's economy. It's a question of economy of hypothesis. Can we reduce it to one change of one parameter? The strength of the strong force, or the distance it propagates in a lattice versus the distance it propagates between single particles.
So I guess I would say I'm not sure. It'd be nice if we had one knob that we can tune.
That's fine, thank you.
Sure. I mean, it would be nice to have a model where we can tune one knob and test along that axis. But I think we're maybe not at that stage with theories, though it would be nice to move in that direction. Yep. Hi, Peter.
John, we have time for one more question.
Sure. Peter.
I very much like your experimental approach.
Thank you.
I wanted to draw attention to a similar experiment by Chris Cooper, who worked with carbon nanotubes. So at some point, chase that down,
okay.
contact Chris or something.
Yeah, definitely. Thank you. Look
He
into it.
saw excess heat with carbon nanotubes.
Okay. Yeah, so not too far afield.
Very short questions. Konrad Czerski, Poland. You have calculated nuclear reaction rates at room temperature. What kind of reactions you might about?
Like for the calculations I showed. So that was considering the simplest of pathways, so hydrogen plus deuterium to say helium-3 or to helium-4. I think
so
if you...
stripping reactions, usual stripping reactions, we know at high energies.
Sorry?
There are some usual stripping reactions we know at high energies.
You mean like an Oppenheimer-Phillips pulling off a neutron or something? Yeah, so I guess I didn't consider that here. It was no neutron model.
It's very important to know what we calculate. So the next very short question, what kind of enhancement you are expecting if you take into account the smearing contribution? So this 1 order of magnitude or maybe factor 2, 3, because in cold fusion and the thermal energies, we change the reaction rates very quickly for many orders of magnitudes.
Yeah.
So per factor 2 and 3, this doesn't change anything.
Yeah, I think that's an excellent point. It's the very nature of tunneling that it's exponential. It depends on tails of the wave function. It's hard to get those things right when it's such a small quantity and everything enters into the exponential. I would say the results here you should take with a very big grain of salt for these calculations. I'm a theorist by trade, so I know to be very skeptical of them. I would say the enhancements that we saw, even going back to Kunin's work, these are 10, 20 orders of magnitude that you would get for the screening. So it really would push us significantly in the right direction just because everything is so sensitive to the knobs that we're tuning.
Okay, we can speak
Okay.
later.
Yeah, thank you.
All right, thank you, John, very much.